In our previous lecture, we discussed Coulomb's law and the definition of electric field, and in that there was a small point which was left out, which was that the expression for the Coulomb's law or the electric field at any point, these expression do not consider the force of a charge on itself. That is, we consider that the charge does not create any force on itself, and it does not come into the expressions. So this is very subtle point, and we will not usually require it to consider it, but we should remember that the definitions of electric field as well as the Coulomb's law do not consider a charge having force on itself. It's like there is a situation that you cannot lift yourself just by pulling your own shoelaces. That is, you cannot do useful thing or create force on yourself. So this was a small point which was left out in previous lecture. Now in this today's lecture we will study or derive the Gauss law in integral form. Before doing that, we need some mathematical instrument. What is that? As we have seen in the expression of the Coulomb's law as well as field, we have to find this R12. Let us say if these are 2 points 1 and 2. So always we have to find this thing R12, and it is usually coming into picture as R12 squared. Okay, so there is some mathematical device from which we can find del R12 and del square 1 by R12, and these two both will be very important in deriving the Gauss law. So let us find first gradient of 1 by R12. So what is R12? Let us say this is point 2 and this is point 1. This is having coordinate x1, y1, z1, and this is having coordinate x, y, z. So what is R12? R12 is x minus x1 squared plus y minus y1 squared plus z minus z1 squared and whole raised to power 1 by 2. So to find the gradient of this 1 by R12, we need to find ax dou by dou x of this whole thing raised to power 1 by 2, and ay dou by dou I of this 1 by whole raised to power 1 by 2, and az dou by dou z of this whole thing, this thing 1 by 2. So let us find for x component. Similarly, we can easily find for the y component and z component. So let us try to find the x component. Ax dou by dou x of x minus x1 squared plus y minus y1 squared plus z minus z1 squared raised to power minus 1 by 2. So minus 1 by 2 will come here, and ax, and on solving it will give me here this thing will come to power 3 by 2, and this will be x minus x1 and 2 will come front. So this will cancel out. So what it is minus ax, x minus x1, this everything was raised to power 3 by 2. Similarly for y we will have minus ay, y minus y1 3 by 2 minus az, z minus z1, this whole thing raised to power 3 by 2. Now if these are 2 points 1 and 2 and the coordinates were x1, y1, z1, and this was x, y, z, so what will be the unit vector between these two? What will be this unit vector? This is point 2. Okay, so what will be this unit vector? It will be simply a12 is equal to x minus x1, the ax vector, y minus y1, the ay unit vector, and z minus z1 and unit vector az, and whole divided by this magnitude of this vector. So it is x minus x1 squared, y minus y1 squared, and z minus z1 squared. So you see that gradient of del or 1 by r12 is simply minus a12 over r12 squared, where r12 is simply under root of x minus x1 squared plus y minus y1 squared plus z minus z1 squared. So this is an important result which will be utilized later on. In the next slide we will find its divergence now. So let us try to find the divergence. Del dot del 1 by r12, what it will be? Dou by dou x of x minus x1, and this was raised to power. In previous slide we could see as r12 squared plus dou by dou y of y minus y1 over r12 squared plus dou by dou z of z minus z1 over r12 squared. Now we can put the value of r12 squared as x minus x1 square plus y minus y1 square plus z minus z1 square. So after putting this and solving, we will find that del dot del 1 by r12 is simply del square 1 by r12 is equal to minus 3 by r12 raised to power 3 plus 3 by r12 raised to power 5 into x minus x1 squared plus y minus y1 squared plus z minus z1 squared. It is found by simply solving this. Okay, now there is a very simple thing. Let us say that this is point 1 and this is point 2. So when these 2 points are not overlapping each other, that is when 1 is not equal to 2, so what will happen? This whole quantity, it is simply r12 squared. So what we will have, minus 3 by r12 cube plus 3 by r12 cube, and it will go to 0. So when these 2 points are not equal, so this quantity is equal to 0. However, when these 2 points are equal, 1 is equal to 2, what happens? That this is minus 3 by 0 plus 0 by 0. So this implies it is not equal to 0. So this is the beautiful thing about it, that del square 1 by r12 is equal to 0 when 1 is not equal to 2 and not equal to 0 when 1 is equal to 2. So this property we will utilize now in deriving the integral form of the Gauss law. So the flux, as we have seen in our previous lectures, is defined as phi is equal to E dot ds over a closed surface S. So let us say this is a closed surface S and this is point charge Q here, and let us say this is point 1 and this surface is let us say at some point 2, let us say we have this point 2 here, x, y, z, and this is x1, y1, z1 coordinates. Okay, now we can write this E as 1 by 4 pi epsilon naught q by r12 squared, or this is a12, or in other form we can utilize our previous derivation only, 1 by 4 pi epsilon naught q, and this is minus of gradient of r12 only. So you see that E can be written as like this, and we can put it in this. So phi can be written as minus of 1 by 4 pi epsilon naught q del 1 by r12 dot ds. Now we can use Gauss divergence theorem to convert this thing into the divergence of something and volume integral. So by using Gauss divergence theorem, we can write it as where we can now use some gradient and the volume integral. So this phi is equal to E dot ds is equal to del dot E dv over volume V, which is enclosed by this surface S. So what we can write? We can write it as minus q by 4 pi epsilon naught over volume V del dot del of 1 by r12 dv. So this is the expression which is for the flux. So now let us write it on the next slide again. So flux is simply written as minus q by 4 pi epsilon naught and volume integral of del dot del of 1 by r12 dv. Now this was the charge q at point 2 and this was the surface. So for all the points on this surface which is enclosing, let us say, some volume, for all the points on this surface we see that this point 1 is not equal to 2. So when this is not equal to 2, this expression in the integrand goes to 0. So you see that phi is equal to 0 if this q is not enclosed inside this surface. However, what happens when this charge q is now enclosed by this surface? Let us say this q is here. So what will happen? Let us see. Now in this case, what we will do, we will define a very small sphere. This small sphere which is now going to enclose this charge q, and this sphere is having a radius of delta r. Okay, so just for this surface s dash, this sphere having surface s dash, we will have to bother about this integral, because for all other points 1 is not equal to 2 and this integral goes to 0. However, just in the case of this delta r going to 0, delta r dash we will write, let us say this delta r dash going to 0, in that limiting case only we have to bother about, because in that case 1 is equal to 2 and we have to solve it further. This integral we have to solve further. So now let us solve just for this very simple very small surface sphere. Okay, so E dot ds for the whole surface is just equal to E dot ds on the small surface actually. So it is q by 4 pi epsilon naught delta r square into 4 pi delta r square. So here what we have seen, that this for this delta r radius, all the points are at delta r, and this ds is simply now changed to 4 pi delta r square, the surface area of this small sphere, and this dot product, since we are assuming that this is a small sphere which is having charge in its center, so the field will be radial in direction, and the surface area, small surface area on the surface of the sphere will also be in the radial direction. So this dot product will have cos 0 is equal to 1. So all this thing boils down to this. So you see that E dot ds for all the surface is simply this is cancelled out, q by epsilon naught. Now you see that this q is the total charge enclosed by this surface. Now this charge can be a point charge, some line charge, or some volume charge density, or some surface charge density. Okay, so this q can be formed by any combination of this. So in a sense, what is Gauss law is saying? Gauss law is saying that the total flux through a closed surface is equal to the total charge enclosed in the volume by that surface, and this charge can be comprised of any point charge or any line charge or any surface charge or any volume charge density also. So we should keep in mind that this expression is going to have only the charge enclosed. And now in the next video or lecture, we will solve some applications, or we solve some numerical examples for the Gauss law. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. And we have created a Telegram channel whose link is given in the description of this video. Please join that for doubt discussion. Thank you.